Let's do the clocks and memory question about Ed Balls. Ed Balls is struggling to learn to dance the waltz. Often he does not even keep in time with the music. His instructor Katya is exasperated but resourceful. In particular, she has a D flip-flop with an output labelled Q2 and a JK flip-flop with an output labelled Q1. For part A, we're asked to give the characteristic table for Katya's D flip-flop. So what do? Well, we tabulate the control signals, they can be 0 or 1, and then we explain how the flip-flop evolves, giving Q2 of t plus 1 in terms of Q2 of t. However, for a D flip-flop, the control signal that comes in at time t is exactly what should come out at time t plus 1, so we just have another copy of the D column in the output. Now for part B, we're asked to give the characteristic table for the JK flip-flop. This time, we should have columns for J of t, the set signal, and K of t, the reset signal. And we should give an output column for Q1 of t plus 1 in terms of Q1 of t. So if we send neither set nor reset, then the flip-flop should stay the same, and we should have Q1 of t as the value of Q1 of t plus 1. If we send the reset signal, but not the set signal, then the flip-flop should go to 0. If we send the set signal, but not the reset signal, then the flip-flop should go to 1. And if we send both signals, the flip-flop should toggle. That's to say, the next state should be the logical negation of the current state. So much for part B. Let's have a little bit more of the question. Katya plans to build a circuit which she can operate with a button labelled B controlling the two flip-flops. The Q2 and Q1 signals select the 2s and 1s bits of a 2-bit number, which appears on a liquid crystal display built into Ed's spectacles. She has matched the clock signal to the beat of the waltz. When Katya presses button B, sending a 1 signal, the display should respond from the next beat by counting 1, 2, 3, 1, 2, 3 to tell Ed when to move his feet. And it should keep counting in that repeating pattern for as long as she keeps the button pressed. When Katya releases the button, putting B to 0, the display should respond by showing 0 to tell Ed he is doing okay. She has sketched out her circuit on the back of an envelope as follows. As you can see, she hasn't quite finished the plan, leaving parts D and E for us to fill in. But first, we're asked to produce a truth table for part C, showing how the circuit ought to behave. So we have 3 columns representing the state of the button, whether she's pressing it or not, and the state of the 2 flip-flops. And we need to explain what state the flip-flops should go to next. So let's fill out the truth table. You can see that it's a truth table, not a characteristic table, because it has columns for the current state as well as for the next state. So, filling in all possible combinations. Let's think about what needs to happen. Well, we've been told that when the button is not being pressed, the circuit should respond by displaying the number 0 to tell Ed that he's doing okay. So that means in the entire top half of the truth table, the next state should be 0. Meanwhile, when the button is pressed, we need to make sure that we're counting 1, 2, 3, 1, 2, 3 in a repeating pattern. So we should map 0, 0, that's the signal for 0, to 1. We should map 0, 1, that's the signal for 1, to the signal for 2, and that will be 1, 0. We should map 1, 0 to the signal, that's 2, for the signal for 3, which will be 1, 1. And then if we have 1, 1, that's the signal for 3, we should send that back to 1, not 0, or we'll end up doing a foxtrot. Now, we've built the truth table that explains how the circuit should step at each stage. The rest of our task is to fill in the missing components of the circuit. So let's see what we have to do. In part D, we can see that we need to explain how to control D given B and Q1 and Q2. And we know that D from this characteristic table should just be whatever we want Q2 to become. That's to say, this column of the truth table tells us what D has to be. This is D of T. Now, how do we compute this? Well, we can see that whenever B is 0, we want D to be 0. And whenever B is 1, there's some other way to compute what D is. So we can start just by using the button with an AND gate to mask the signal that is sent to D. Putting this AND here means that if B is 0, there's definitely a 0 here. But now, what's coming in to the other part, the other input of the AND? So if B is 1, this signal is what will be transmitted to D. That means we just need to look at this part of the truth table, and we should recognize that this is the behavior of an XOR gate. That tells us that the remaining part of the circuit is just XOR. So much for part D. How about part E? Well, we again have to control J and K in order to get the Q1 behavior we want. What Q1 behavior do we have? Well, let's see. Looking at these two lines of the truth table, we can see that we're definitely, in this case, resetting the flip-flop. So we want to make sure that J of T and K of T are both 0. No, we don't. We want to make sure that we send the reset signal. Similarly, in these two lines of the truth table, again, we definitely want to make sure that we reset, so we had better send the reset signal. In these two lines of the truth table, we can see that if Q1 was 0 or 1, it ends up being 1 or 0. So that means we definitely want to toggle the flip-flop. And finally, in the bottom two lines of this truth table, we can see that whatever Q1 was, we want it to end up setting the JK flip-flop. So J should be 1 and K should be 0. So now we can see how, given the B signal and the Q2 signal, and that's what we've got to work with, we know how to set the J signal and the K signal. All right. Looking at the truth table, we can see that J is exactly the same as the button signal. So straightforwardly, we can do this much. Now looking at the K column, we can see that we have exactly the behavior of a NAND gate. That is to say that the K signal is the result of NANDing B with Q2. Fine. We've completed Katya's circuit. Good luck, Ed Balls.